Hi, your goers! Welcome to the exam for review videos. You finally made it. Just know that it's all going to be over at the end of this week, and you did something that most people can't do, and it's just amazing that you've gotten this far. So definitely congratulate yourself on that. But you're not out of the woods yet, so make sure you watch these videos and get down these last few concepts, and let's just begin. So we're going to just start with a couple of recall concepts. So the first thing I want to talk about is this notion of conjugation. And I use this term like rush pi sig. It's like rushing this fraternity. So if I were to have some sort of like linear chain like this, and I were to classify the types of bonds, going from left to right, I would say that this is a pi bond. Oops, it's a pi bond. This is a sigma bond, and that's another pi bond. So the trend of conjugation is pi, sigma, pi, sigma, pi, sigma, or in other words, just rush pi sig. So that's what I like to say for people to remember conjugated systems. So this is a fully conjugated system because it's pi, sigma, all the way out, but you could also have systems that are partially conjugated, so something like that. So this diene would be a partially conjugated system because I have pi, sigma, sigma. All right, so it's partially conjugated on the right side, so it's more stabilized on the right side than the left side of the ring, but it's still conjugated. So what is this notion of conjugation? Why does it really exist? Well, in a pi sigma orbital overlap, we're going to have something that looks like this, and I'll just draw the sigma bond framework. So the sigma bond framework looks like this. If I draw a p orbital here, and then I'll draw a p orbital on this one, and a p orbital on this one, and I'm just going to color that in to see the phasing. So these overlap, and these overlap. So you can see that in addition to the sigma bond framework that I drew, this would be a pi bond, and that would be the second pi bond. So since conjugated systems have this pi sigma pi arrangement, basically any given electron, so if I drew an electron in purple, it can flow all the way across the molecule, back and forth, because we have all of these pi bonds connected in one kind of linear fashion. So that is the notion of conjugation. We have this extra stabilizing feature of delocalizing pi electrons over the entire molecule as long as I have pi sigma pi. So that's what conjugation is. All right, so that's the first review concept that I want to talk about. And the next thing I want to talk about is the very first reaction we learned in organic chemistry. So it actually kind of makes sense that we're ending organic 2 finally, and we're revisiting our very first reaction, so it's kind of like a nostalgic moment for me. But first, you know that we have this pi bond that attacks this hydrogen, and then it kicks off that bromine to form a bromide anion. So we are going to follow Markovnikov's rule to form the more stable carbocation, or the more stable intermediate. So I have a choice. I have a choice over, and let me make this smaller. I have a choice over here at the tertiary position, or I have a choice over here at the secondary position to place that carbocation. And we said that tertiary carbocations are the most stable because of hyperconjugation, whereas there's that partial donation of alkyl electron density to stabilize that carbocation. So we are definitely going to follow Markovnikov's rule by forming this tertiary carbocation intermediate. And then I just have excess, not excess, just bromide in solution, and then that can attack that carbocation to form, this product. And it's not racemic because we did not, we don't have a chiral center at that position. All right? So there we go. So that is we are reviewing those concepts, and just remember that we are prone to all those carbocation rearrangements that we saw, like hydride shifts, alkyl shifts, ring expansion. So just be cognizant of that. So now we're going to take this step further. We're going to do hydrohalogenation of diene, and we just want to kind of look at this first reaction scheme before we even consider temperature. So we have over here, we have 2 different pi bonds. So if we were to classify all these different carbons, this is a primary carbon, a secondary carbon. Over here we have a secondary carbon, and we have a tertiary carbon. So clearly I'm going to pick the alkene that's on the right side to form my carbocation, because we're going to form the more stable intermediate. And when I'm doing so, this may not have been obvious at first, so if I were to draw the mechanistic arrows over here, we have this choice of either forming the carbocation at the tertiary position, or this isn't just any secondary, this is secondary allylic position. So the second, we said anytime we have resonance with a carbocation, that is more stable because we're delocalizing that partial charge over a larger area, not just a single, spot on the molecule. So actually, we're not forming the carbocation at the tertiary position, we're forming an allylic carbocation. So it would look something like this. All right, and that allylic carbocation can then, resonate, and we can now have bromide or chloride in this sense adding at two different positions. So I'm just going to draw the resonance structure, and I'll draw those mechanistic arrows in red. If I were to draw that, the product of that mechanistic step would be something that looks like this. All right, so you can see based on which resonance structure I use, I could have bromide adding either over here or bromide adding over here. All right, so we're going to see that in the following two examples where we had the same molecule, but now we're going to do something with temperature and consider thermodynamic or kinetic control. So again, we're over here at this position. We decided that we're going to form this, intermediate, where the secondary allylic carbocation is formed. But now we have to worry about this notion of temperature. So negative 78 degrees Celsius is something called kinetic control. We saw that when we were doing Claisen reactions. We were discussing that notion. So when we're under kinetic control, we are going to form the fastest product, not the most stable product. So this was the carbocation that formed first. We don't have any time to do any resonance. So now this chloride is just going to come in and just attack, and that's going to be the end of my reaction. It's forming the fastest. So we are going to get this product. Okay, and it is racemic at that position, so we would have wedge and dash configuration, all right? So that is what forms the fastest. We don't have time to do that resonance. That's how I kind of think about it, and I will talk about the temperature with the next step, all right? The reason why we're calling this a 1,2 product is, if you recall, we added the hydrogen over here, so if I call that carbon 1, and then we added the chloride over here to carbon 2, so that's the 1,2 product, or the kinetic product, if you see that on the exam. All right, so now let's move to the 1,4 product. So this is thermodynamic control. So if I were to form that same carbocation intermediate, where we have the secondary allylic carbocation, what's going to happen is now thermodynamic control, I want to form the more stable product. So not necessarily the fastest, but now I have more time to actually do this resonance arrows, like, do this whole resonance step. And I am going to use this step. So we said that thermodynamic control is the more stable product. So what can I think about is, why is this structure more stable than this structure? Well, if you said alkene stability or alkene substitution, you're correct. So if you classify this alkene on the left with a kinetic intermediate, that's going to be a primary, or a mono-substituted alkene, and now over here you have a di-substituted alkene. So we definitely have a more stable product. So now that chloride anion can just come in and attack at that position. So even though our carbocation went from a secondary allylic to a primary allylic, we care more about alkene stability than carbocation stability in this situation. So our end product is going to be something that looks like this. All right? So that is the thermodynamic product, and then this is the chloride product. So now this notion of temperature. So basically the reason that we are dealing with temperature is it's all about energy. So when I have 40 degrees Celsius, I have more energy in my system, so I have more energy to do that extra resonance step. That's how I think about it. At negative 78 degrees Celsius, I don't have enough energy to show that resonating step, so we're just going to form that chloride at that immediate carbocation that we form. And that's pretty much it. That was pretty simple, I think, a hydrohalogenation of dienes, just to be cognizant of thermodynamic and kinetic control. All right, so now we're going to move on to the second half of Chapter 20, which is pericyclic reactions. So, there's many different types of pericyclic reactions that are in organic chemistry, but we are really only going to deal with something called Diels-Alder in a second. So this is something called the diene over here, okay, because we have two pi bonds, and this is called the dienophile, and that will make sense in a little bit. So if I were to draw my mechanistic arrows, and this will also make sense in a little bit, we're always going to have the diene, or electrons originate from the diene, form a bond with the dienophile. Then that pi bond breaks off and forms a new bond here, but we exceed the octet at this position, so we also have to move that pi bond over. So it's the cyclic array of electronic arrows, and it's all a single-step concerted mechanism. So if I were to draw the end product of that, I would see a product that looks like this. So we form cyclohexenes when we do these pericyclic reactions, cyclohexenes. So definitely be cognizant of that in synthesis. If you see a cyclohexene, you probably did a Diels-Alder. All right, so if I want to just draw the transition state, I think transition states are important. I want to draw the sigma bond framework. So that's the sigma bond framework. And all bonds that break or form have to be partial bonds. So this pi bond, in this top left corner was broken, so we're going to put dashes there. but then we formed a new bond. You know, we saw that new bond forming right there, but we also broke that pi bond right there, but we did form a new bond here, and we also broke that pi bond there, and we formed a new one there. So our transition state should be, you know, this cyclic array of dashed lines, because that is a pericyclic reaction that goes into a circle. So definitely be cognizant of our intermediates here. I think that's kind of important. I'm sorry, our transition states, and be cognizant that we are going to form these cyclohexene end products. All right. So now on to Diels-Alder. So we have a couple of considerations that we want to do. So the diene, the dienophile. So we just looked at what those were. So dienes need to be electron rich, and that's why we showed the mechanistic arrows originate from the diene and go to the dienophile. By proxy, that means that the dienophile has to be an electron poor. So the way that we can do that is by adding specific functional groups that are either electron donating groups, that's what EDG stands for, or electron withdrawing groups, which is going to pull electron density away. So if I were to give you some examples of electron donating groups, you know, I could have, you know, something that looks like that, like an alcohol. I could have, you know, an amine, something that looks like that. I can have, you know, an ester that looks like that. I can have an amide that looks like that, you know. So the common trend in all of these, and I'll highlight it, is that the heteroatom that is attached to our diene, so I'm assuming that, you know, this area is my diene, you know, what's connected to it. The heteroatom has lone pairs that it can donate into the ring into the diene, excuse me, via resonance, and that's donating electron density to make it electron rich. So that's what an electron donating group would be. So if I were to think about some electron withdrawing groups, the first thing I think of is a nitro group. So that may not be obvious. So this is our heteroatom and nitrogen, and we normally think that nitrogen has lone pairs associated with it, but if I were to draw out the Lewis structure of the nitro group, you can see that I don't have any electrons available on nitrogen to donate in. So that's why a nitro group would be considered an electron withdrawing group. All right. So then we could also think of, like, you know, maybe an aldehyde bounded to something, a carboxylic acid bounded to something, an ester bounded to something, you know, an amide bounded to something. So any of these would work, you know, I'm sure there are more, but the whole purpose of this is you can see that there are no electrons on that heteroatom, there aren't really heteroatoms there, but on that carbonyl to donate into the ring. So what we have instead is induction. So this induction, or this dipole moment, is what's pulling electron density out of that dienophile and making it electron poor. All right, so we typically see, you know, on dienes electron donating groups and dienophiles electron withdrawing groups, and that should kind of make sense there. So just a notion I want to kind of point out real quick is if I looked at, you know, let me change colors over here. If I looked at this amide versus this amide, the only difference is the position of the nitrogen and the carbonyl. So if the nitrogen is oriented in front or directly adjacent to a diene, that's going to be an electron donating group. But if the nitrogen is farther away, you know, we have that carbonyl directly adjacent instead, and that's going to be an electron withdrawing group. So just be cognizant of how those positions are located. All right. So the next thing about dienes and dienophiles is that the diene must be able to adopt something called the S-cis conformation. So all that means is that the S stands for sigma bond, and cis, we learned that all the time before, and cis just means on the same face. So basically, we need to be able to have a diene. So if I had this diene, let's just say it's something like this. Oops, that's the wrong thing. If I had a diene that was trans, so something like that, this is the S-trans conformation. So let me zoom in over here. So the S-trans conformation basically says this. This is my sigma bond, so that's the S, and around that sigma bond, so if I were to draw an imaginary line through it, we have a trans arrangement of my double bonds. So that is S-trans. But then, we said that back in Organic 1, we have free rotation around that sigma bond. So can I rotate to form the S-cis conformation? Well, yes, I can. So this is the S-cis conformation. So if I were to find that sigma bond, all right, and then this would be, you know, the cis arrangement because those alkanes are on the same base. So that is the S-cis arrangement. So dienes must be able to adopt that S-cis conformation. That is the reactive conformation for Diels-Alders. All right. Another thing we're going to talk about with the dienophile is something called the endo rule, and that basically just means that the substituent, or the electron withdrawing group, on that dienophile is going to end up on a dash orientation, or it's going to be on the opposite face of the newly formed ring. And we'll talk about that in a second. Actually, this semester we're doing something differently where we're not talking about molecular orbital theory with that. So that's what used to kind of explain why the endo rule happened. So I'm not going to do that for this video. But if you would like to, you know, understand really the organics behind it, I would definitely advise, you know, opening up our textbook, reading that little section on, you know, the highest occupied molecular orbital and lowest unoccupied molecular orbital. It definitely gives you a little bit of context and why we're doing this instead of just memorizing. All right, so then finally, stereochemistry is retained in the diene, so the outer substituents are going to orient downwards on dashes, and I have a good graphic in a second, while the inward substituents are oriented up on wedges. So what do I mean by that? So if I were to draw my diene in this S-cis conformation, and I were to have a substituent there and a substituent here, this substituent that I drew over here is going to be considered inward. So this is an inward substituent. And this one is going to be considered outward. So those inward substituents are always going to end up on a wedge, so that's going to go to a wedge, and we'll explain that in a second. And that outside substituent is always going to go onto a dash, all right? Always. So then, when I talk about my dienophile, the stereochemistry is retained as well. So if it's cis, if my substituents are cis on that dienophile, then they're going to be cis on my product, both dashes. If it's trans on the dienophile, then they're going to be trans on the product, so one wedge and one dash. And that's what we mean by Diels-Alder being a very, very highly stereospecific reaction, because not only is the stereochemistry of the diene retained, but also of the dienophile. So let's just go over here. I put this exam question, and I think it's important for you guys to understand, because I'm pretty sure you'll get something like this on the test in some way or form. Rank the following dienes in order of their reaction rate with the dienophile and Diels-Alder reaction, 4 being the fastest and 1 being the slowest. So clearly, we're going to look for electron donating groups on all of these first. So clearly I see that I have electron donating groups with oxygen heteroatoms attached on all of them, so they are all electron donating in some way or another. So we basically don't have any difference in that. But what next we can consider is, can these dienes adopt the S-cis conformation, which is the reactive conformation needed to react in a Diels-Alder reaction. So let's just go through these and find our sigma bonds. So this is on my sigma bond right here, so sigma bond. And if I can, look around the sigma bond, I see that I have this imaginary line, and they are trans to one another. So this is definitely an S-trans arrangement. More specifically, can I rotate any sort of way to get to the sigma framework? And no, I can't. So this is called S-trans, but more specifically, locked. This is the worst thing you could have, a locked S-trans arrangement, because there's no reaction at all with the Diels-Alder. So immediately that's going to be number 1 for us. All right? Let's just move on over here. So let's classify, the easy geometry of these alkenes. So if you look over here, this is a Z alkene, excuse me, and another Z alkene. So this is my this is my sigma bond right here, and around this imaginary line, we see that we definitely have the S-trans arrangement, all right? But can I rotate to get to the S-cis conformation? Well, yes, I totally can do that, so that's going to look something like this. All right, and then it's going to look also like this. All right, so I want to make this point right here. Do you see how I drew this? This is my sigma bond, same sigma bond. And when I rotate inwards, I see I have this huge steric clash between that ester functional group and that methyl group. So this is, even though it can adopt the S-cis conformation, it's sterically crowded. Sterics. So this is, let's just say, let's do a sad face. Not good at all. It's very bad sterics, but let's compare the other ones first because we need to see that arrangement. So over here, we have a Z alkene, and over here we have an E alkene. And if I were to draw my sigma bond right here, and this is my framework, down this bond, you definitely see it's in the S-trans arrangement right now. But when I rotate, I'll have something that looks like this. I'll have the methyl group in, but I'll have the, methoxy group hanging outside. So even though this is the S-cis arrangement, we don't have that steric clash as much as we did. We only have that methyl group kind of crowding that area, not both substituents. So that's evident over there. So not so bad. So let's just say so-so. All right? So then over here, we have an E alkene and another E alkene, and this is my sigma bond. So we definitely have the S-trans arrangement as well. But when I show, the S-cis conformation, both of those methyl groups, one of those methyl groups and then this ethoxy group both orient out, so the S-cis conformation is observed, and there isn't any steric hindrance, so this is the better one over there. So number 1 is the worst, we said that over there. We said S-cis with sterics is probably the next slowest, followed by this one, and then finally followed by this one. Now, even though I hate telling you to memorize, but I can show you this relationship right now. We have 2 Z alkenes, 1 Z, 1 E, 1 E, 1 E. So clearly E alkenes are the better ones when we're thinking about the reactive conformation. Here you see we have 2 E's, we have 1 E, 1 Z, and then 2 Z's, and you can kind of follow that trend. Those E alkenes kind of orient away towards one another, so we don't have those steric hindrance that's going on. All right, definitely be aware of that. That's something that we would definitely test you on. All right. So here's that graphic of why do those inward substituents, orient outwards on wedges, and why do those outward substituents like A and D end up on dashes? So if you were to see, this is kind of the reactive conformation. I think of my diene with those substituents as a gate, like I'm a car and I'm entering a gated neighborhood or something like that. So this is, my dienophile approaching the diene. And as it approaches the diene, you can see that we have to push over here these substituents out of the way for that, for those bonds to form. So when this, dienophile approaches, we have to open up the gate. So think about it. So my car is approaching the gate, and I have to get through somehow. So the only way to do that is to push those gates up, to push B and C up on wedges. So that's why B and C end up on wedges over there. And by proxy, that's going to force A and D down on dashes. So if I were to just draw, kind of in plain how we're used to seeing it, so if I draw these two substituents, and my dienophile was coming in, we would understand that, this is my just regular framework, that this methyl group that's oriented, inward has to be pushed up to let that dienophile in, so that's going to be a wedge. And then over here, that other methyl group that's oriented outwards was pushed down because this hydrogen was pushed up. So you can show, hydrogen there, and then that methyl group down. So that's what the stereochemistry with respect to the diene. All right, so I would definitely not do that. And there is one more product. If we show the other orientation, so it would be that methyl and that dash, but they are that. All right. So that is what I wanted to talk about in terms of stereochemistry, and then we're just going to see the endo row when we do some example problems. So I think I have like 7 examples that we can work through below, and that will be the end of this video. So let's just start with this one. So I just want to start off by saying that on your exam, you are going to have one of your molecules be symmetrical and one of them will not, all right? Or they can both be symmetrical, but we will not give you 2 unsymmetricals. So by that, what I mean is like my diene is going to have a plane of symmetry and my dienophile is not, or my dienophile will and my diene won't. One or the other. We're not going to give you both 2 unsymmetrical things because you can get 4 possible regioisomers, and that's just way too complicated for you guys. All right, so this is my diene, and it's attacking my dienophile. So I think the sigma bond framework is very easy for you guys to understand. Like, clearly it's this bond forming here, and then that pi electron's being forced out to go there, and then those pi electrons forming a double bond over there. So this kind of arrangement, I think, isn't too complicated to figure that out. It's just kind of figuring out what my stereochemistry is going to be. All right, so the endo rule, and I'm going to say this without, a lot of explanation because we're not going to go into the molecular orbital theory, but those substituents that we see are going to end up on dashes. So these 2 esters are going to be on dashes because they want to be on the opposite side of the newly formed ring. And the logic behind that is basically the dash configuration of that dienophile is a favorable interaction with a newly formed pi bond when the transition state. And I know that really doesn't make much sense, but if you understood molecular orbital theory, it would. So just note that when you have these newly formed products, we're going to form, these are sp3 centers, so we want to figure that we want to put them on dashes. That follows the endo rule. So you can show that, and then you can show that. All right, and this is a meso molecule because we have a plane of symmetry. So there's only one product, meso. So when there's symmetry in both of the molecules, we're always going to get one product that's meso. And then when there's not symmetry with one of them, we're going to get 2 products. And we'll see that in a second. All right, so we're going to get more and more complicated as we go. So I don't think that was too bad. So now we're going to go over here. So we're going to just show those, cyclic mechanistic arrows. So I think the sigma bond framework isn't too bad. All right, so then over here, we just have the substituents. But do I put that nitrile group or that methyl group on wedges or dashes? Well, no, because clearly I just formed, when we have triple bonds, alkynes, we have that double bond still there, so that means that this nitrile and methyl group are still in plane, so there is no stereochemistry considered. Well, that was easy. Move on to the next one. All right, so here's that first example where we don't see a symmetrical thing. So if I were to draw a plane of symmetry, either way, there is no symmetry there. So this is where we need to consider 2 different approaches. So we have to consider the dienophile approaching in that conformation right now, and then we also need to consider, the dienophile approaching in this conformation. All right. So we just basically pancake flip it, and we have to consider, both approaches whenever we have non-symmetry. Okay. So basically, what's going to happen is we're going to form that cyclohexene over here, and one of those, so since it's trans in this dienophile, we're going to have a trans arrangement over in our and our end product. So we can show that that ketone, is going to be on a dash over there, but then this ketone is going to have to be on a wedge over there. So the way that I'm envisioning that is I'm picking up this molecule, and I know you can't see my hand right now, but I'm picking up that molecule on the paint, and I'm rotating it 90 degrees to the left, and I'm slamming it on top of the diene. So that means that if I took this one, it's going to be inward. That's why it's a dash. And then this one is going to be on a wedge. That's going to be sticking up. I take my hand, I'm going to picture that's my molecule, and I rotate it 90 degrees to the left, and I slam it on the diene. That's what I'm thinking of. When I think about the other approach, it's going to be the same thing, but just the wedges and dashes are going to invert. So again, take that molecule as if it was your hand, rotate it 90 degrees, and place it on your diene. So then clearly that ketone is going to be sticking up, and then that ketone is going to be sticking down. So that's why you have to consider both approaches, because you can see I have two distinct enantiomers from this approach. So this is my two answers. All right, that's the first thing we saw with symmetry. So remember, the stereochemistry of the diene and dienophile are retained. So if I saw a trans dienophile, I would expect a trans arrangement of my substituents in my end product. All right, so now we have this situation where we have a closed ring, and we're going to form something called a bicyclic compound. So we saw this a little bit in organic 1. We didn't really think too much of it with the nomenclature. But we are going to form, these mechanistic arrows. Okay, so that is going to form a structure that looks like this. And I'll draw the 3D one first. There's multiple ways you can do it. So I like these 3D drawings. I think it's cool. So what happens is that this CH2 group is going to be puckered up, which is over here, because that dienophile approaches from the bottom face. Like we saw it, back in this graphic. I'll come back up to here. That dienophile approaches from the bottom face, so it's going to push anything out up. All right, so that happens over here again. So it's going to push or pucker that CH2 group up into 3D space. And then we're left with, okay, where am I putting those CN groups? Well, remember that they are cis in this product, so that means they have to be cis in our end product. And more specifically, we follow the under rule. We're going to put them on dashes, all right? So don't think too much about it. So I'm just going to put CN. I'm going to put CN. Those are oriented down. And you can show, like, those H's sticking up if you want to, just to be, like, clear in your answer. All right, so that's one way to show it. But you could also show it from a top view. So the top view is just drawing that cyclohexene. And you can draw the CH2 group, sticking out into plane by forming these two, wedges coming and meeting together. And then I can show CN on dashes and CN on dashes. So those are equal. So that's the first time we saw a 3D type structure. All right. And that's that. So there's no other, structure that we're going to observe because we have symmetry with both of our molecules. So remember, only one product when we have symmetry of both the diene and dienophile. All right, so let's move on to more complicated ones. So now we're actually going to consider the substituents on the diene, which we haven't done before. So again, we draw these arrows, really easy to show the mechanism. And what's going to happen is since this dienophile does not have symmetry, we have to consider the alternate approach as well. So we have to consider this approach. All right, so if I were to consider this approach, remember we form these cyclohexenes, and if it's on an outside configuration, remember the gates, so if I had these hydrogens kind of sticking in, those hydrogens are what's going to stick up to let my dienophile come in, and then those methyl groups are going to be forced down. So we're going to get both of those methyl groups on dashes, and then we're going to think, okay, we're going to observe this ender rule, so those, that ester is going to be on a dash configuration. All right. Again, if you imagine picking up this molecule and you, as if it was your hand, and rotating it 90 degrees to the right and slamming it on top of that diene, you could observe that that ester group is going to be on a dash. Now, if I consider the other orientation, we're still going to get, that cyclohexene with both methyl groups on dashes, but now just the position of that ester is going to change. So now we have two different regioisomers. So that's why we have to consider two different approaches. They're the same exact molecule, and they're not the same molecule. They look the same, but you see that the ester group has changed positions. Now, if I were to pancake flip this molecule and rotate it 180 degrees up, you would see that you would get the same molecules above, but that ester would be on a wedge configuration. So that's why sometimes we see the term, racemic or plus enantiomer, because, we get that alternate configuration when we consider the alternate approach. Right? I like to just draw both products anyway on the test because, I like to consider both sterically arrangements of that, but you can write that if you want to. All right. So now we're over here where we have the situation where now we have one inside substituent and one outside substituent. So again, that inside substituent is going to be on a wedge and that outside is going to be on a dash. So if I were to just draw, this cyclohexene, this methyl substituent is going to end up on a dash, and then that methyl group over here is going to end up on a wedge, because remember that gate has to open up. And then we're just going to draw both of our esters following that interval. Since they're cis in our dienophile, we're going to have cis observance over here. And since there's no symmetry in our diene, we have to consider the other approach. So that approaching, this molecule. All right, so then if we were considering that approach, it's just the same thing as before, but now we're going to have inversion of our center. So now we're going to have a wedge, a methyl group up there, a dash over here, and then we're going to have, still those esters over there. I don't think it's too bad to understand the stereochemistry. I can definitely see how it's challenging, but definitely, go over your rules and that will make sense. So that is the end product over there. And finally, we have this last funky one. So we have symmetry with our diene, but no symmetry with our dienophile. So we need to make sure that we consider the alternate approach of, this kind of arrangement. Okay, so with this kind of arrangement, you see that our sulfur group is kind of in the way, so that thiol group is going to have to be puckered up into plane. So if I were to draw, the arrangement of that, I'll do it in 3D first. You can draw it like this. All right, so that S group is sticking up now. We have this alkene, so don't worry about up or down orientation of these methoxy groups, since that we're connected to a double bond. And then now we have to consider this cis-trans arrangement. Well, there's no choice. So in this first arrangement, we can say that this carboxylic acid is down, which means that hydrogen has to be up. But since it's trans in my dienophile, we have to show the other one up, and then the hydrogen down. So that's the first regio isomer. If I wanted to draw the second one, let's draw that. Okay, we have these methoxy groups that stay in plane. And then we have to switch our orientation. So now this carboxylic acid is up, and then this one's down. All right, and those would be my two regio isomers of that. And if I wanted to do a top-down view of this, it would be something that looks like this. This would also be equivalent. MEO, MEO. We're going to show wedge, wedge, and then put an S in the middle. And then we're going to show one of the Qs, or carboxylic acid as I call them, like that. And then you're going to show the other one. Sorry, I'm drawing this really fast. And then, we're just going to invert those centers. So now this is going to be a wedge, and that's going to be a dash. All right? And that pretty much covers, I showed every single example of, with respect to showing symmetry, not showing symmetry, showing triple bonds, showing, different functional groups, puckering up into 3D space. I think that's everything in Chapter 20. Diels algebra is definitely the most challenging thing on this exam in terms of stereochemistry. Just watch this video a couple times and you guys will be golden. All right, Chapter 21 and 22 videos will be coming out shortly, and you guys are going to kill this exam. Good luck.